Find the relative maxima minima of f of x equals x times the cube root of 16 minus x. So the first thing I'd like to do is define the domain of this function, which in this case is all real numbers. Now, why is that? The part of the function x that, takes any number, not an issue. The cube root of 16 minus x, that takes anything as well. You can take the cube root of any real number. If it's positive or negative, it doesn't matter. So yeah, in total, our domain, there's no restrictions on either part of this function, so our domain is all real numbers. All right, next thing is this. We want to go ahead and, this is a calculus class, this function is differential. I'm going to take a derivative here of my function. Right, because when we're looking for relative minimum and maximum, we have to find places where you have critical points, right? So go ahead and do that. Sorry, let me just rewrite the function. And the 3 should be more up here. Okay. All right. So if we take a derivative, I'm going to have to use my product rule, because it's a product of two functions. So the product rule says hold the first function, and so it would be times the derivative of the second. So if you go ahead and use you'd have to use the chain rule on this. You would get something along the lines of 1/3 16 minus x to the negative 2/3 times minus 1 plus, then I hold the second function, the one I just took the derivative of, and take the derivative of x, which is just 1. And that would be my derivative, and I'm going to clean this up a bit. And I would get minus, and what I mean by clean up here is as follows. I'm going to rewrite this term with positive exponents only. Now, let me just rewrite this as an x. You could have left it with negative exponents if you wanted to, but I prefer myself just to work with positive exponents. Up to you, though. And I'm going to simplify this expression just a bit by getting a common denominator. And I'm going to rewrite 16 minus x. The cube root of 16 minus x is 16 minus x to the 1/3. And the reason I'm doing that is when I get the common denominator, it'll be more clear what my result is when I do the arithmetic here. So hold on for that. So the common denominator would have to be the 3 times the 16 minus x to the 2/3. So that 16 minus x to the 1/3 would be multiplied by 3 times 16 minus x to the 2/3. So you get minus x plus, we add these exponents together, you get 3/3, which is 1. And yeah, the reason we get 1 is because we're multiplying two exponents up here with the same base, that base being, I could do a better job on the 2/3, 16 minus x, so we can add the powers together. And yeah, I would have f prime of x equals, putting everything onto one denominator, be that. And finally, if you distribute that 3 and add that minus x, you would get minus 4x plus 48. Now, if for critical points, there's two types. Where the derivative equals 0, that's what we call a stationary point, and where the derivative is undefined, but for which f of x is continuous. So for our case, when the derivative equals 0 for that first type of critical point, first of all, we have a fraction pretty much for our function. It's one function over another, not a rational function though, because it's not one polynomial over another. But when you have a fraction equal to 0, this equals 0 if the numerator equals 0. So if you solve that, you will get 12. And where's the derivative defined for which the function is continuous? That would be at 16. Because if you plug 16 in for f prime, well, you can't, because it makes that undefined. So that's where the derivative is undefined. And but you can plug it in back into the original function, and it would be continuous there. Okay, that part's okay. So those are our critical points. Now, what do we do? And let me just circle this. That. Now, what do we do in terms of finding whether these are relative, mins or maxims? Well, you have to make a number line. And the reason the domain was important here was because if I had a domain that was not all real numbers, then I can't pick anything that I want. So there'd be a restriction in terms of numbers that I could pick to test out whether I have a minimum or maximum. And what I'm going to do is this. I'm going to pick points that are in like these intervals right here. So let's say something like 0, on this number line, something that's less than 12, something between 12 and 16, 13, and then something greater than 16, 17. What I'm going to do with all of those is I'm going to put them into your derivative, and I'm going to go ahead and calculate what you get for each of these. And, well, be more specific, I'm going to calculate the sign of all of these numbers. So any one of these numbers is either going to give me a negative or positive. The derivative equals 0 at 12. So there's no places other than that where the derivative would equal to 0. And the 16, the reason we're interested in that is because it changes the sign. So that's why we put that in the number line. Anyways, so I'm digressing here. So you get 48 over 3 times 16 to the 2/3. All I know is that that's positive. If you plug 13 into your derivative, that'd be minus 4 times 13 plus 48. That'd be like a minus 4 all over 3 times 3 to the 2/3. And that would be less than 0. And if you plug in 17, negative 4 times 17 is negative 68 plus 48, that's a negative 28 over 3 times 16 minus 17 is negative 1 to the 2/3. That'd be less than 0 as well, because negative 1 to the second power is positive, and the cube root of that is something that's positive. So what do all these numbers mean? Well, what all these numbers tell you is what the sign of whether your function is going to be, the derivative is positive or negative. And we can interpret that as whether the function is increasing or decreasing. But it also tells you where you're going to have a relative min and max. So at 0, we got something that was positive. And let me use red here. What that entails is for any number that's less than 12. 0 was just our test point, but you could have picked any point other than 0. For any number less than 12, your derivative will be positive. For any number between 12 and 16, your derivative is negative, so I'm going to put these little minuses here. And after 16, you get minuses as well because of the signs that 13 and 17 gave us. All right, so what do we have? Well, we only have one extrema here, which is at 12. X equals 12 would be a relative maximum. MUM here. Because what happens is, let me zoom in here, your function's increasing, stops at 12, the derivative is 0, and then it goes back down. Okay. And the way you would find the location of that point is, so yeah, when I say is a relative extrema, it's really a location. Okay. The actual value of the point here, the actual y, is when you plug 12 back into your original function. And if we did that, you'd get 12 times the cube root of 16 minus 12, which is 4. So that's where your relative maximum will occur. And 16 itself is nothing. Your function is decreasing at 16. And 16 itself, that is what we would call a vertical asymptote, okay? And your graph at 16 would look something like that. In fact, why don't we take a look at that using Desmos? Where are you, Desmos? There we go. And if we look at that graph, that would be y equals x times 16 minus x to the 1/3. Okay. So we take a look at this graph. This is what we have. And at 12 up here, 12, 19.049, that's where your maximum occurs. And then over here at 16, 0, that's where you have your vertical asymptote. That was just, sorry, your vertical tangent line, excuse me, is the word. So at x equals 16, you have a vertical tangent line. All right. And that would be it for that. So only one relative maximum. You don't always have to have a maximum or minimum. And yeah, sometimes you can get stuff like vertical tangent lines. You can also get these things called cusps. But in this case, it was just a relative max that we got. All right, well, thank you for your time.